Hello everyone, my name is Amjad. Today I'm going to present you my paper which have the title of Design and Simulation of Grid-Connected Photovoltaic Solar Carport System and study its feasibility for Libyan Telecommunication Company. Outlines, Introduction, System Sizing, which include design methodology, configuration check, performance analysis, protection, and rating factors, simulation and results of Scenario 1 and Scenario 2, financial analysis, and conclusion. PV systems are silent, non-polluting and sustainable source of power that convert the sunlight to electrical energy. Therefore, we take advantage of these traits by design PV system which aim to be installed at the carport of the Libyan Telecommunication Company with two different scenarios of installations and different numbers of PV modules according to the direction of orientation. Each scenario has two different cases. In each case, PV panels tilted in different inclination angle. The presentation will illustrate the first case of each scenario due to the presentation's time limitation. The paper presents simple approach for the design and simulation of PV system with help of many software packages such as PV Solar Premium, Voltage Drop Calculator, AutoCAD to draw the support system at installation site in real dimensions. The system sizing finds the number of series modules per string, total number of strings, PV system protection from shadows and their effects over current and voltage surges, the performance analysis by finding some factors which indicate system state. All the previous have been calculated by considering the impact of ambient temperature and solar radiation on the solar system. Design methodology, system sizing. Since the output power of the PV system is profoundly affected by the temperature of the solar due to variation of the PV panel's open circuit voltage and maximum power point voltage, so the effective cell temperature can be found with using this formula by knowing of module voltage at STC, voltage coefficient, and considering that the voltage of the PV panel does not affected by the solar radiation, so the solar radiation consider it as at its STC conditions as 1000 watt per meter squared. So we can calculate the minimum allowed number of modules in the string by calculating the maximum power point voltage of the module at the maximum temperature, and by knowing the lower limit of the inverters from the inverter specification by considering DC voltage drop in the cables and taking 10% as safety margin from the lower limit of the maximum power point tracker of the inverter, so we can find out the minimum number of the PV modules per string, which 19 modules. With the same way, we can calculate the maximum allowed number of modules per string by find out the maximum power point voltage of the inverter at the minimum ambient temperature, and by knowing the upper limit of the inverter's maximum power point voltage from the inverter specification, we can calculate the maximum number of PV modules per string, which is 20 modules per string. Now we find the value of the open circuit voltage of the PV panels at lowest temperature. To check which is suitable as a configuration, 19 panels or 20 panels per PV string, and by considering maximum DC input voltage of the inverter from the inverter's specifications, which is 1000 volt. Then we find that 19 panels per string is the best option because the input of the open circuit voltage is 960 volt is less than 1000 volt. PV system protection. PV system need to be protected from shadows and its effects. Since all the PV cells are connected in series, the shaded cells won't be able to produce as much current as the unshaded ones. Therefore, the hotspots will be produced on the module due to the power dissipation in form of heat. The picture shows the using of infrared to illustrate hotspots, and these are the effect of hotspots may cause modules cracks. Therefore, the bypass diodes are attached to eliminate the hotspot phenomena. Moreover, the insulation diodes, or what known as blocking diodes, are placed in series in each PV string wherever the array consists of two or more parallel branches to prevent the current generated by other parallel connected PV panels in the same array flowing back through the weaker or shaded string. Circuit breaker or fuses are commonly implemented to provide protection against the thermal effects of overcurrent. The fuses used to protect string. The rating of the fuse should be higher than the short circuit current of the string at STC conditions. Load break switches used to protect the whole array. The rating of the disconnector should be higher than the short circuit current of the array at STC conditions. Since PV installation exposed to overvoltage that may occur due to lightning operation and incidents in the network, so PV installations provided by surge protection devices and the ground system should be equipotentially bounded. Performance analysis. Performance of PV systems can be measured by calculating some factors such as performance ratio, specific energy yields, capacity factor, and system productivity, the energy produced per square meter, and how many kilowatt hours can we get from each kilowatt peak. Durating factors, which are factors reducing the PV system productivity, such as standard test conditions. Any deviation from the standard test condition will reduce the system productivity. Also, some factors related to the manufacturer, temperature, dirt and dust, mismatch wiring losses, and DC-AC conversion efficiency. All these factors have been considered in this. Scenario 1. The panel oriented to the south directly as shown in the figure below. Scenario 1 system setup. Number of PV modules have been used more than 2100 PV panel. Total installed capacity more than 690 kilowatt peak. Number of inverters, 4 inverters have been used, 177 kilowatt each. By knowing the total number of PV panels, we can calculate the total number of PV strings, the total number and the total number of strings each inverter. So the PV generator array is 19 rows, 28 columns. Since the current varies significantly with the solar radiation, so it's inconsiderate in computing number of modules. By knowing the PV system array configuration and the rated power of the PV panel, we can calculate the maximum input DC power for each inverter, which is 172.9 kilowatt peak. That is less than the input power of the inverter, which is 177. Then the design in safe range. The figure below shows the single line diagram of the scenario 1. Scenario 1 case 1. PV panels oriented to the south, azimuth 0 at tilt angle 15 degree, which is the maximum inclination angle of the support structure due to the mechanical consideration. Energy produced by PV system more than 1.2 gigawatt hour a year. Performance ratio was 80% and CO2 emission avoided more than 700 tons a year. Scenario 2. The panel oriented as shown in figure below, with the deviation from the south by 67 degrees. The advantage of this orientation is allows us to install more support systems compared to the first scenario. That reflects to raise the total installed capacity of the PV plant. However, It has a disadvantage that the panel deviates from the optimum azimuth by 67 degrees. All the design configuration that mentioned before applies in this scenario as well. Scenario 2 system setup. Number of PV modules more than 2,300 PV panel. Total installed capacity was more than 770 kilowatt peak. Number of inverters 5 inverters, 177 kilowatt each. Number of strings 25 string, 19 PV panel per string. The figure below shows the single line diagram of the scenario 2. Scenario 2 case 1. PV panels tilt angle was 15 degree. Maximum inclination angle of the support structure. Energy produced by PV system was more than 1.25 gigawatt hour a year. Performance ratio was 79%. CO2 emission avoided was more than 740 tons a year. Financial analysis. Electricity production cost is equal more than $0.18 per kilowatt hour. The price considers generation, transmission, distribution, also losses which occurs in each stage. Since telecommunication company that system designed for is Libyan Telecommunication Company, therefore it supplied with electricity with subsidized price, which is 0.48. Therefore, both prices, official and subsidized, are taken into consideration as conversion in this financial study. The table below shows financial analysis of the scenario 1 by calculating many different factors such as capital cost, electricity production cost, net present value, net future value, annual average money saving, and payback period. And this table shows scenario 2 financial analysis by considering the mentioned factors. Conclusion. Saving in energy contributed to the company's load and reducing the emission of greenhouse gases are the most important concerned results, as relative conversion between the cases of a study by considering factors of analysis PV system performance, specific energy yield, performance ratio, capacity factor, energy produced per square meter of PV generator. The first scenario is technically more efficient and more cost effective than the second scenario. However, the latter is greater than the first scenario by more than 80 kilowatt peak. By comparing between case 1 and case 2 in the first scenario, the performance of case 2 is better due to the inclination angle of the PV module optimum angle tilt angle in Libya. On the fully contrary, the second scenario due to the deviation from the south orientation by 67 degrees. The effect of PV panel orientation on their tilt angle is regardless when quantified performance ratio of the PV system, where its value affected significantly by ambient temperature, so its value falls down during the summer months and vice versa for winter. The average annual saving for money for telecommunication company is more than $150,000 with calculating by official price and more than 52 for subsidized price in scenario 1, and for scenario 2 more than $155,000 and $53,000 respectively. Thanks for your attention. Let me know if you have any questions.